Okay, so the first speaker of this afternoon is Peng Shan from Tsinghua, and she's going to talk about modularity for W-algebras, affine string fibres, and associated varieties.
Thank you for the introduction. I'd like to start to thank the organizers for the invitation. So I've been spending quite some time during this program, and I'm enjoying a lot. And then I apologize to those who have heard this talk not too long ago and not too far away. Anyways, so yeah, so what I'm going to talk about today is first based on joint work with Wenbin with Dan Xie and Wenbin Yan. Our colleagues at Tsinghua, and then there's a second part about who I did there. About the associated variety is joined with Wenbin Yan and Qixian Zhao. So I will start by trying to explain some motivations from physics for this work. First, talk about my collaborators. Nice spelling. All right. So we start from the four-dimensional n=2 superconformal field theory. Then there were several people. Which is called 4D-2D duality, where they associate a 4D theory of 2D object, which is a vertex algebra. And then the Higgs branch is conjecturally the Higgs branch of such a theory is supposed to be let's say you have a theory and then you have a vertex algebra, and this is supposed to be given by the associated variety of this vertex algebra. This is proved in some cases by Arakawa. And then inside the 4D theory, there is a particular class which is called class S theory, which comes from the 6D theory, putting R3, 1 and the Riemann circles. And then for these class S to work by Gayotto, Moore, and Nash. Which explains the Coulomb branch for such a theory should be given by the moduli space of Higgs bundles on the corresponding Riemann surface. So so this is Higgs bundles on Riemann surface. And so for today, what we're going to be interested in is a class of a certain class of theory, which is called Adjurant-Douglas for generalized Adjurant-Douglas theory. Where what appears for the vertex algebra side is some Lie theoretic object that we would like to study. So so here what appears is for example L kappa, it's a simple quotient of universal affine vertex algebra. Or their Drinfeld-Sokolov reduction, which give you some W-algebras. Okay, and then what appears on the Coulomb branch side will be some Higgs bundles. So this will be this. P1 but with some level structure and with regular singularity at 0 and the irregular singularity at infinity. And then by some sort of duality or some sort of duality, you want to relate properties on the Higgs branch side to those which on the Coulomb branch side. And so this is a sort of relation we're interested in. And then one of the work, which is, well, okay, maybe that is Frickson and Knights have previously established for W-algebra in type A of and for the principal W-algebra, which is they call in their language is W and minimal model. For this case, they find a bijection in between C star fixed point in the Qixian fiber, in the Qixian fiber here. And irreducible representations of these W-algebras. And then what we wanted to do is to generalize this to other types. And so here is the plan of this talk. So first of all, I want to explain a similar bijection for any affine algebra. At a so-called boundary admissible level. And then, so the characters of these boundary admissible representations have some modularity property. And then inspired by the relation between these representations and the relation to Qixian fiber in particular, like I'll be working with the affine spinor fiber, and there's some relation to double affine Hecke algebras, and so we give an interpretation of the modularity of characters of admissible representation in terms of data. And then I want to explain how the reduction to W-algebra goes. And then hopefully I'll have time to explain a conjecture about associative variety for a more general cases, for some non-admissible representations, which give you some new give some new cases where give some understanding about it. All right, any question before I really start? Okay, so let me just give some reminders about admissible representations. So let's fix G to be a finite dimensional complex simple Lie algebra. For the sake of simplicity for this talk, I will assume it's simply less, but actually for most of For 1, 2, 3, they no. Yeah, for 1, 2, 3, they will be working for general. And then I fixed H to be a Cartesian subalgebra. Then this denote G had the affine algebra with the central element C and then we have the universal affine vertex algebra, which is just as the representation is the induced module from the finite from G, the positive half. This one-dimensional representation where your element central element X at K or kappa. So Cx. And then so this is a universal affine vertex algebra, and it has a simple quotient, which is both a simple quotient as a module and a simple quotient as a vertex algebra. So this is the vertex algebra whose representation we're going to be interested in. And then we'll impose some condition on the level. This is this admissible representation. So we fix kappa to be boundary admissible. That means kappa plus the dual Koxler number is a rational number have the form H check over U. Where U is a positive integer and co-prime to H check. And then it turned out that the representation of this vertex algebra L kappa at this level. So from now on, U can be arbitrary, but I will fix always kappa of this form. So if you consider those modules in the category O of the affine algebra, which are actually modules for this L kappa, so it's inside the category O. This form a semi-simple category. And then the simple objects are the so-called admissible representations. So they're highest weight simple modules, and then the highest weight have the following form. So with lambda so-called admissible weight. So this is the set of weight of level kappa, and then you require its regular dominant. And then the integral co-roots for lambda, like those co-roots which are integral with respect to lambda, form a root system which is isomorphic to your initial co-roots. And this set has been, so this notion was due to Katz and Wakimoto. So they first studied these representations, and then have classified what are the admissible weights. And so in this boundary, case, it can be described as follows. So it's always of the form of an element W in the extended affine well group. So W semi-direct product with a co-weight lattice dot action on kappa times lambda 0, where lambda 0 is the 0th fundamental weight. But if you want to make sure such a weight is dominant, you need to impose some condition, and the condition is that W sends a particular subset of co-roots to positive co-roots. And here, chi check U is, so you take all the simple finite co-roots. And then for alpha 0 check, normally you have it should be like C minus the highest co-root theta check, but here you do minus theta check plus U times the central elements. So this is the description of this set of admissible representations, and we want to have a bijection of this set with fixed points in the Hecke fiber. But actually, instead of Hecke fiber, I'll be talking about the affine Springer fiber, and which actually lie in the Hecke fiber physics our study, and this is a result due to Bijection code, Wenbin, Michael McGrain, and Zhuoyan. So yeah, so let me introduce the affine Springer fiber. We'll be interested in. So in this case, I'll just take G tag to be the non-admissible. Of G. And then I'll take G check to be the corresponding group of adjoint type. And then I fix Borel and Poisson. And parts. And then we'll consider the affine flag variety for G check. Quotient by Ewald-Horry subgroup. And then this thing is not connected. The connected component is indexed. Yeah, so let's call this group omega as some outer automorphisms of the affine. And then we're going to consider the a Springer fiber here for the following element gamma. So gamma will be, so I take the sum of root vectors for all the finite roots. So because here now roots will be the co-root there. So yeah, the notation are compatible. So this is and then I'll take f beta times t to the power of u. So this is an element here. It is so-called homogeneous elliptic element. Yeah, so the affine Springer fiber we'll be interested in is the sub-schema. So I'll take the reduced one inside the affine flag variety consisting of those whose close points is described as follows. So if you do a joint G inverse epsilon gamma, you require belongs to the VN graph. And since, well, yeah, okay, so gamma is homogeneous, what does it mean? It means, or more like it implies that there is a C star action on this fiber, which is given as follows. You have a C star mapping to T check times the loop rotation. So T check just acts on flag by left multiplication. And then the loop rotation C star will just dilating this T variable. And then if you consider, so that you have a sub C star, which is given by sending a variable Z to Z, the image of Z under U times rho, where rho is now a co-character for T check. And then Z to the power of H check. Then you can check that the adjoint action of the C star will dilate this gamma. So the gamma is homogeneous for this action, and therefore it acts on right. So the right hand side acts on the flag, and then the sub C star will stabilize the fiber. And so we get a C star action on this fiber, and And since this character is kind of regular, actually you can check that the C star action, the C star fixed point is isolated and it lands inside the T type fixed point of your affine flag variety. And this is naturally identified with the extended affine well group. And then you only need to check. So if we want to parameterize elements here, you only need to check which of those like satisfied this condition. And this is exactly the same condition as what's happening here. So like using this interpretation of the Hecke fiber in terms of, well, I guess you can do this for Hecke fiber as well, but for a fine spinel fiber, it's more straightforward. So you get the desired bijection in this case. So the claim is we have a natural map from this set of fixed points to the set of admissible weights just by sending an element W to W inverse dot action on capital lambda 0. It gives a bijection between so actually there will be some coincidence when you apply when you do the dot action on the weight, and but if you restrict it to the connected component of the fiber and then take the C star fixed point, this gives a bijection to the set of admissible weights. Okay. Yeah, as a remark, so this, like I said in the beginning, I only discussed like simply list, but actually this is quite general. This works in general if you take for any affine algebra, including the twisted ones, but for any, how to say, for any let's say L kappa of P hat, the bijection is between admissible representations and fixed points in the fiber, in a similar fiber for the Longland's dual of the affine algebra. So it can be yeah, if you started with a non-simply laced usual affine algebra, you would need to consider the fiber for the twisted affine algebra. Okay.
Could I ask you to clarify the assumption on gamma? So like L here is the rank.
L is the rank of G, yeah, and then
Its principal.
yes, yeah. If you take T equals 0, you get the principal nilpotent.
Can you say anything beyond that?
I will hopefully, if I have time at the end, about non-admissible cases. So yeah, so here this U is the one as in the definition of the kappa. All right. Now let me move on to other questions. Let me move on to the modularity part. So for all the admissible weights, well, for representation of a function, where you have a renormalized character, which is a function on the affine certainly part of the affine carton. And so this is e to the 2 pi I times tau as lambda, and then you take trace on L lambda of an element in the carton. And then here V is an element in the following subset. In the so I will by Z tau and T belongs to sorry, so Z tau and T. Why did I write it? 2 pi I Z plus T times C minus tau times D. And then Z is an element in the finite carton, and tau and T are complex numbers, but you require the imaginary part of tau is constant. So the characters are meromorphic functions on Y, and you have an action of a network action of SL2Z here. And what is proved by Kac and Wakimoto is that the span of these characters form a vector space, which is invariant under this SO2Z action. So here is an action of SO2Z. And moreover, so this group is generated by the S and T matrix, and you can describe how these elements acting on these basis elements. Like the matrix coefficients can be written explicitly. And on the other side, so like affine Hecke algebra is coherent, like K-theory of Sternberg was discussed this morning. And then there's a similar realization to Weisrow of double affine Hecke algebra as a sort of K-theory for affine Sternberg, right? It's an equivalent K-theory for affine Sternberg, right? Maybe I should do G10 with the necessary C stars. And therefore, in this picture, this algebra has a module which is given by the K-theory of the fine Springer fiber we're considering. So you consider the equivariant. So maybe let me put it this way. So okay, so you have double affine Hecke algebra, and there is some localization here which are not very precise. And then, well, so it has two parameters. I don't want to go to the definition for double affine Hecke algebras, but so for those who know the theory, like so we assume that the parameters satisfy the following condition, like t to the power of h check is q to the power of minus u. And then when we do this specialization, let me just denote this algebra by h kappa, and then it will act on the K-theory of equivalent K-theory of this affine Springer fiber, where I localized this C star. And so since gamma is elliptic, this is a projective variety. So this is actually a finite dimensional representation for this double affine Hecke algebra. And let me denote it by V gamma. Actually, this representation is very particular. So it has been studied by Cherednik before. So V gamma is so-called perfect representation. in sense of Cherednik. It satisfies a list of conditions which makes it similar to a Berlinda algebra. And what is particularly useful for us is that Cherednik defined an action of a central extension of PSL2Z as projective automorphisms of H, let's say H kappa. And then it induced, and so it induced a projective automorphism of this particular representation D gamma. So you have some modular group acting on this finite dimensional representation coming from this Daha theory. And then what we wanted to do is to compare. So because we make the relationship between admissible representation and its fixed points, and the K theory. Okay, so yeah, maybe let me say one more thing. This is just a finite set of points. Okay. And so by localization theory, this is the same as the K theory of the fixed points. So this is nothing, just functions on this finite set. So this space is just function on this, and therefore I have a basis just be given by the characteristic function at each of the points. So for each of oh, did I change my picture? So okay. And then and so we can also describe in a similar manner the generator of this, the ST generator here, acting on this basis. So this is given in terms of some evaluations of some McDonald polynomials. And the second theorem we show is that this is with Qixian and Yan, is that so now if I set the Cherednik parameter to be root of unity related to kappa, so kappa times minus H check over U. And in this case, by the relationship I was imposing here, this actually implies T equals to 1. Then I have a isomorphism of vector spaces between this one, which is spanned by the characters of the admissible representation, and the one on the fine superior fiber side. So I just set up this isomorphism such that it matches the bases in the following way. So if I have, yeah, maybe I use W as a notation as I did before. So it will send this high characteristic function basis to the characters of the module given by this this bijection, so which is W minus dot kappa lambda 0. But I need to correct it by some sign. So I need it to be multiplied by the sign of a finite part of W. So, yeah, maybe swap in right LW. So this is some particular, well, you can choose a well, there, yeah, I just omit some detail, but you can choose a presentation of W in an appropriate way, such that yeah, you take you pick the finite. Yeah, we write it as finite group element times some translation, and you put a sign. The statement is that this isomorphism of vector space commutes with the SL2Z action. Actually, initially here you only had a PSL2Z, like the central extension of PSL2Z action, which maps onto SL2Z. But you can check in this case, it actually factors through and both sides have SL2Z. Okay. Any questions? Okay. And I can move on to the W-algebra part. So I'll pick F to be a nilpotent element of G. And then I assume that, so for now we assume F admits a book even grading. But maybe this condition is not necessary. But for now we just, well, if you don't assume this, you'll probably need some twist for the correct bijection. But so we do this for the moment. But one more serious assumption is that we assume that F is regular in the baby. So this will be used later on. And then so let me denote the by L. And then so the W-algebra we'll be interested in is obtained by the so-called actually, yeah, there are two versions of Drinfeld so-called reduction. And this is given by the plus version. But anyway, so we have a it's given by the Drinfeld so-called reduction of this simple vertex algebra L kappa. And then you can also do reductions on modules. But in order for your reduction to have good homological property, that means if you want it to be an exact functor, you should take the other version of Drinfeld so-called reduction. So it's the minus version. So this is the minus reduction functor. It goes from L kappa module to representations of this vertex algebra, this W algebra, and it should satisfy a list of properties. But for now, most of this are, well, for now this is still conjectural in the most general case, but I will comment on which cases are known later. So this is a conjecture in the original form is due to Katz, Run, and Matsumoto. Yeah, there's some ambiguity about which W algebra you should take, but then actually for the form I'm going to write down, it's communicated to us by Arakawa. Okay, so what's the statement? The statement is that if you take an admissible representation here, so lambda, let's write lambda equals to W dot kappa lambda 0, which is admissible. Then the reduction of such a the module L lambda is either 0 or simple. So first statement is of L lambda is simple or 0. And then you want to know when it is not zero, and this happens only if and only if. So if you take this W, applying to the set, like how you check I had at the beginning, this is positive affine co-roots, but which lie outside the co-roots for the co-roots for the living. And finally, it could happen that you have two simple modules which reduce to the same one. And this happens if and only if lambda belongs to the orbit of lambda prime under the dot action of the Well-group formulation. So WL is Well-group. And so this conjecture is known in the case when F is principal. So this is due to Arakawa. And for any G, and then it's known for any F in type A. So this is again due to Arakawa. And then it is also known for a so-called exceptional pair. So yeah, there's a particular set of conditions on F and the level, which I think the condition is that the like the reduction of the W-algebra is extremely simple in this case, but I forgot the exact. Anyway, this is Arakawa and Hecke. I hope we hear. Sorry, I forgot. And then right, and then Gerbier Dillon claims well, at least he announced in some talks he has approved for this in general, but this is not something we have looked into. So assuming this conjecture, like what I want to explain is how this description of simplest for the W-algebra is compatible with reduction on the fiber side. So on the fiber side, when you have a W-algebra, you will consider this partition variety, where you so you fix a Levy subgroup of G check corresponding to the Levy over there, and then you fix P check a parahoric subgroup of inside G check O, such that the Levy factor of P check is M check. And then you can consider this for the same gamma, you consider this this partition version, which this lives inside G check the portion type. And its close points are of this form. So now we require G inverse of gamma belongs to the radical of G check. And as before, you will still have the same C star acting on this partition variety. And you can imagine that, so if you compare the conditions, the radical of P check is inside the Euler-Haury. So when you impose this condition, you will remove some of your fixed points. And this corresponds to to this condition, so you will have some W which doesn't satisfy this condition. That's precisely what you remove here. And then since here you're doing quotient by p-check instead of the Uehara, you will have like 2 points in the original Springer fiber, which will be well, if they're in the preimage, will be mapping to the same point here. And this is the same condition as when does the reduction of the two simple modules coincide. And so so in particular we can deduce from, so assume this conjecture holds. Then the bijection before, then we have bijection. Between irreducible representation of the W-algebra and fixed points of this bijection fiber. Again, you take connecting components and you take fixed points, which is induced by the bijection. And then interesting consequence is that this gives a way to compute the number of irreducible representations for the W-algebra. So this tells us that so we can deduce from this that the number of irreducible representations for this W-algebra is given by the following formula. So it's 1 over the cardinality of the variables for the Libby, and then you do U times L is the rank minus J. I will say what is J later, and then our product of I equals to 1 to J, U minus EI. So here, E1, EJ are the exponents for WL, the Libby, the wild group for the Libby. So this formula is given by counting the fixed points here. So there's some work
So gamma is as before, but P check depends on F.
Yes. So yeah, F is regular in the Libby for P check.
And but gamma was
Gamma is the same.
What happens if U is, if it is negative, this product? I mean, U could be less than Hochstetter number, or is it not allowed?
Just a second. We don't. What happens? Okay.
U was co-prime to the Hochstetter number.
Yeah, U is co-prime. But somehow yes. Then there's no representation for the W-algebra. Like yeah, U equals 1, then like all the reduction dies. So.
But not if that's not 1, but bigger than 1, but still co-prime.
Yeah, I think what will happen is like if this number is negative, then there's just no representation. For that. Yeah, I'll think about it.
Actually, it's not clear. So there are interesting things like with tilting modules, for example, for quantum group.
Yes.
If order of the fruit of unity is bigger than Hochstetter number, then we know exactly what happens. But if order is less, then it becomes a bit more complicated.
Wow.
And so there are. So maybe it's only valid this formula.
Yeah, maybe we need. So, but on the right-hand side. Okay, I don't know with that. There's no representation, but
Okay.
that's true. I didn't. Okay, and then finally, so we can. So for the SL2Z action, what happens is that you can similarly looking at the space spanned by the characters. I will just put an F here. So this is the characters for the simples of the W-algebra. And then, so it still carries an action of SO2Z. And on the Daha side, what you can do is you consider the following space. So our V gamma before was a representation for Daha, but I have specialized this Daha to t equals to 1, and in particular, it contains the group algebra for the finite well group. And so I can consider the sign idempotent for this WL, and then I take this, let's say, a partially spherical or anti-spherical subalgebra, and this acts on E minus of EL minus of this V gamma before. And it also inherits an action of TSO2Z, and then the statement is you have a natural, so yeah, you have a natural the isomorphism before induces an isomorphism between VKF and V gamma P check, which is compatible with SO2Z action. Okay. So, okay. So maybe I just have a remark that for F principle for W and minimal model. So identification of these SL2Z action for Daha and for those appearing in the W-algebra context was also appeared in recent work of book of correlative. Now, and all right. All right, if there are no questions, I'll pass to associated variety. Associated variety. So all these things about admissible level is nice, and so kind of understand them now. And but you want to know, like the question was asked, like how do you go beyond the admissible levels? And more particular, like for other levels, what are the L kappa which appears in the image of this 42D duality functor? And one of the hints is that physicists, they expect that this Higgs branch have finitely many symplectic loops. This corresponds to a condition which that if it is the associative variety of some vertex algebra, then this corresponds to the condition that this vertex algebra is so-called quasi-Lees by deflection. So the question you want to ask is for which kappa is L kappa quasi-Lees? It is known that they're not always quasi-Lees. So, but here somehow our proposal is given by this relationship, and then we think maybe you want to look at other elliptic fibers. So the elliptic fiber we're looking at has a particular slope, which is u over h check, but you have other elliptic fibers which correspond to other elliptic numbers. And so we just try to study them. So yeah, it's kind of motivated by this question. Yeah, like one consequence of quasi-Lees, this would imply that L kappa has only finitely many highest weight simple representation. And so if you start from this philosophy that we expect that if you take kappa to be some so you put some elliptic number here and some other u which is co-prime to it, and then m is some other elliptic number. And you look at representation, irreducible representation for these L kappa. We expect they should be in bijection with the connected components of the fixed points in the corresponding spring or fiber. So we have a gamma m for this m, and then you take C star fixed locus, but now you may have some, it's not isolated, you may have some higher components, but you take we did a couple of examples, and we think what it looks to be true is that the connected components of C star fixed locus is in bijection with irreducible representations of L kappa.
Can you remind this Higgs branch? I thought that in most cases it is known to have finitely many leaves. Yeah. Like when moment map is flat, for example, isn't it known in this case that it has finitely many?
Higgs branch.
Higgs branch is just you take a symplectic representation of some group and do this Hamiltonian reduction. Yeah?
Yes, and
So,
like my physics not very like 3D and 4D have the same Higgs branch. Then probably they would just Okay, so you propose to remove it?
maybe well, I mean under some conditions. I think.
Right. Yeah, right. So but I'm not sure in this case it's given by Hamiltonian reduction of some. It's not clear to me.
Okay, so these are not like random.
Huh?
These are not like random theories, so they're not sympathetic. When you say the Higgs branch is a sympathetic reduction,
They are not
that's
reduction.
for big 3D theories which have a random, which are labeled by open representation.
This is more general.
This is these are not for such type.
Okay.
Yeah, okay, and in any case, so we propose to study this kind of situations, and then we want to propose the following a conjecture for their associative varieties. It's given in the following terms. So Lustig defined a map from conjugacy classes in the finite Weyl group to a set of nilpotent orbits in the I'll take it this way. So and this map has a different inscription and some minimal reduction due to in Zhiwei Yun's work. And then our elliptic element gamma m, it corresponds to some elliptic conjugacy class here. And so in particular, under this map, it gives you some particular nilpotent orbit. So let me denote this by O gamma. And then there is a duality map, which, there is this Barber-Slogan-Lustig static and duality from the nilpotent cone of the non-admissible Lie group to nilpotent cone of the Lie group initially. And then what we want to conjecture, so this is joined with Yan and Qixian Zhao, is that so for my kappa as there, so kappa plus h check is an elliptic number divided by u. So m is elliptic. Then the associative variety for this L kappa is the closure of this the image of this orbit under this. And we have a few, like we checked all the examples where this site has been computed. So which, covers the following list. So known examples. So the first case is for all the admissible case, this is true. So for the admissible case, this was computed by Arakawa, and then this side is also computed exclusively, and so you can see there that they match up. And then second case is what we call subcoxillary case. In this case, this refers to the elliptic number, which is just the one next to the coxillary one. And in this case, this is the regular orbit, and this is the closure of the minimal orbit. So this is true. And also for a series of elliptic number in type D, so you take type Dn, where n is even and m equals to n. This is a particular case of the elliptic number. Then the associative variety is also computed. It corresponds to the closure of this orbit. This is by Moreau and Arakawa. And then yeah, and in this case it matches as well. Right. And for example, if n is odd, then this is no longer elliptic number, and in that case, you can see that there's the algebra is not quasi. It's not the vertex algebra is not quasi-means. All right, I'll stop here. Thank you.